Swayam Prabha. Digital India. Educated India.
Welcome to this new segment of CD spectroscopy and Mossbauer spectroscopy for chemists. My name is Arnab Datta and I am an associate professor in the Department of Chemistry at IIT Bombay. So, in the previous segment we are discussing about the relationship between chirality and symmetry. So, let me just refresh your memory a little bit. Chirality and point group. And the take home message from this particular segment was a molecule can be chiral if it does not have any SN axis. So, the presence of SN axis is directly connected to chirality. Why? Because when you define chirality, we say we are taking a mirror image, that means a reflection, that means a reflection around a plane. Basically we are doing a sigma operation. Then we take this mirror image and try to fit whether it fits with the original molecule. Now over here we are doing nothing but simple rotation around an axis. So you are basically doing a sigma operation and Cn operation without really understanding it. So basically we are nothing but doing a Sn operation. So if the molecule does not fit on its original position or original structure, that means you do not have an SN axis, that means you are going to have a chiral molecule. So that we have found, and then if you also find out this can be simplified, that means S1 means sigma plane. So that means if you do not have a sigma plane, there is a chance that you are going to be chiral, and S2 is center of symmetry, that means there is also a chance you have a chiral molecule if you do not have a center of symmetry. But just simple absence of this particular symmetry element does not guarantee that you are going to have a chiral molecule. If you have this particular symmetry elements, then it is guaranteed that your molecule will not be chiral, that will be achiral. On the other hand, we try to find out what are the point groups are present there that they do not have any particular SN axis, and we figure it out, that is belongs to two groups Cn and Dn. A simple axis rotation group nothing other than Cn axis, and a dihedral group nothing other than Cn and n number of C2s perpendicular to the Cn. And I want to mention C1 is a special case of Cn, where you have nothing but only an identity operator available for a particular structure of the molecule. So, with that covered, then today we are going to cover 3 different structures of molecules and find out how they are becoming chiral. So, let us go ahead with that. So, the first example we are going to take is the following: an iron octahedral complex, and over here I am going to have bidentate ligands bind to it. What do I mean by bidentate ligands? So, this structure I am drawing like this, it is nothing but carboxylate acid groups. So, over here in a carboxylate binding group, you can see these are the 2 centers where it will bind to the metal, and over here it can bind with 2 different coordination sites from the same ligand. So, that is why they are called the bidentate ligand. And over here this iron is binding 3 such bidentate ligand. Now, the question is whether this molecule is chiral or not. and as we learned earlier, what you have to do, just figure it out, what is the point group of this molecule. So, let us figure it out, and we have learned that earlier. Is this molecule linear? Answer is no. Is this molecule belong to octahedral or tetrahedral point group, that means any cubic group? So, the answer is still no, although you will say that this molecule is binding in an octahedral geometry. That is true, this molecule is binding in an octahedral geometry, but that does not mean that the molecule is octahedral symmetry, because to have an octahedral symmetry, the molecule should possess a center of symmetry, and for center of symmetry, that means if you go from one part of the molecule to the other part through the center of the molecule, which is iron in this case, we will have to find a similar molecule or segment present. So, for an example, if you take this oxygen, go through this, you can find an oxygen. So, it is valid, oxygen to oxygen valid, oxygen to oxygen valid, but there is also some molecular portion present between this oxygen. This is this carbon carbon bond. If you go through this, you do not find any. If you go through this, you do not find any, same thing. So, that means this molecule does not belong to octahedral point group. Now, the question comes, what is the CN point group present over here? So, this molecule actually has a C3. So, where is that C3? So, to do that, I am going to draw this molecule in this particular format, the front one separately compared to the background one. So, you can see these are the different ways the molecule can be showed. So, the back one is actually the blue for each of the segment, and it should be this kind of wedge bond. So, these are the ones. So, each of the bidentate ligand, you can see there is two part of it. One is the front part, one is the backward part. For example, over there this particular segment, this dot, this line actually says that this molecule is actually on the plane of the paper, this bond, whereas this dotted wedge line says that it is below the plane. So, that means among these two, this is above, this is below. Same thing over here, this is above, this is below, this is above, this is below, relative terms. And over there they are connected through carbon carbon system, and over there you can see they are not finding any other segment on the other side. So, they are not really octahedral symmetry. But if I now rotate it over here, just connecting the front parts for all this molecule along with the backward parts for all this molecule, you can see you are seeing two triangles, and that means that if I rotate this molecule through this iron 120 degree, I am going to get all the backward oxygen exchange places and the frontward oxygen exchange places, but the molecular structure will remain same as the original one, superimposable and indistinguishable with this particular rotation, and this rotation is nothing but a C3. So, that is where the C3 exists in this particular molecule. Now, the next question, whether I have n number of C2 perpendicular to Cn, so that means do I have 3 C2s perpendicular to the C3 or not. If I can find one, the others will be there. So, for that again I am drawing this particular molecule. Just the oxygen and then do the connection, and this molecule you can see if you rotate through this carbon bound system over here, which is connected to the oxygen, and over here if you rotate 180 degree over here or C2, this oxygen goes over here, this oxygen goes over there, and their connection will also pass on, and these two oxygen stays it is on their place, iron is remaining on the same place. So, with that we can say this is actually having a C2 present over there in the molecule, and if you have found one C2, because it is perpendicular to C3, you are also going to find the other two in a similar position, that means through this oxygen oxygen carbon carbon bond of a oxalate ligand. So, that is present over there. So, yes, we have 3 C2 perpendicular to C3. Next question is, do I have a sigma h? Sigma h, there is the C3 will be on the perpendicular plane, and you can see it is obviously not there because the front and back is not going to exchange. So, that is no sigma h. The question is, do you have 3 sigma d's? That means the sigma d will be present in between the C2s, and if you try to put a sigma plane over here, you can see obviously it is not going to work. So, that is why, so somewhere in between this C2 it is not going to work because oxygen will come on the other side, there is nothing there. So, that is why it does not have also sigma d's. So, what I am looking with, no sigma d, no sigma h, 3 C2 perpendicular to C3, only Cn. So, this molecule belongs to the point group of D3. So, that means this molecule belongs to point group of D3, and as we learned earlier, this molecule will be chiral in nature. Now, the question is, what will be the 2 enantiomers? For that, I am going to draw this molecule one more time. And what you need to do, find out what is the front part of a bidentate ligand and what is the background part. So, this is I am putting as O1 O1, or I should say OA OA, OB OB, OC OC. That is because of our understanding where the molecule goes after a particular rotation or not. They are not like different oxygen atoms, they are all very similar and equivalent. So, now what we do for each particular bidentate ligand, from the front to back we find out which side I am actually rotating. And for that, what I am going to do, for this bidentate ligand over here, this is the front side, this is the back side. So, front to back, if I want to rotate, I have to rotate in this particular direction. Similarly, for this part, this is the front part, this is the back part, I have to rotate in this direction. Again, for this one, the C1, this is the front part, this is the back part, rotate this direction. So, you can see the rotation remain in the similar direction. It is like this, a left hand side rotation, and this particular side rotation is called a lambda isomer. That means what happens to the other portion of it, that let us take a look into it. So far we have how to find the different isomers of this kind of D3 molecule and what is the nomenclature is going to come. So, we found that is actually from front to back for each set of bidentate ligand. Every bidentate ligand have 2 sides, front and back. Go from front to back, front to back, front to back. You see it is similar rotation on this direction, that means it is a lambda isomer. Now, let us take a mirror image of it. Because although we know it is a D3 point group molecule, so it should be chiral, but let us double check it. So, over there this octahedral geometry is going to remain same. So, first let us draw that and then try to fill the molecule. So, it's mirror image. So, this particular portion over here will come closer to the mirror, because that is closer to the mirror in the beginning. So, that is there. OB on the top, OC on the top is going to remain as it is. This OC over here is going to come on this side. And the remaining will be the OB, and then the connections are going to be like this. So, now you can take a look into it and try to figure it out how it is going to work, and you can see front to back for this side is this one, front to back, front to back. So, you can see all of a sudden my rotational system is changed, and this is known as a delta isomer. So, these are the two different isomers we can actually find in this particular set of the molecule. And now we are going to look into a different variants of this particular molecule. So, that will be our number 2 examples, where we are going to use glycinate as a ligand. So, what is glycinate ligand? It is nothing but coming from a natural amino acid glycine that we will cover in the next few segments. So, this molecule glycine, this is the structure CH2 and then they showed him carboxylate and ammonia. So, this molecule typically bind with this ammonia and carboxylate. That means it can also act as a bidentate ligand, but over here a subtle difference, not both the atoms are same. One of the coordination atom is nitrogen, one of them is oxygen. So, let us take a look into it. So, let us take similar iron complex, and over here I am not mentioning any oxygen state or anything, just looking into the coordination geometry at this moment. So, over here I can say that nitrogen and oxygen can be like that, nitrogen and oxygen like that. So, this is oxygen, sorry, and there is other nitrogen and oxygen. So, that is how it is, and I just want to put this one as oxygen, this one as nitrogen. So, nitrogen in the front part, oxygen in the backward part for each of this ligand. So, over here you can see also nitrogen and oxygen is going like this. So, it is actually a left hand rotation, but before going to what is the nomenclature of this particular enantiomer, first find out whether it is an enantiomer or not. For that we need to find the point group. So, again we ask the question, are you linear? Answer is no. Are you belong to a cubic group, that means tetrahedral or octahedral? The answer is no. But over here be very careful, because when we talk about this tetrahedral and octahedral, we are talking about the symmetry, not about the coordination geometry. Coordination geometry is still octahedral, but its symmetry, which is the more important thing in this particular aspect, that is not perfectly octahedral, because over here you can see all the coordination atoms are also not same. You have 3 sets of nitrogen, 3 sets of oxygen. So, that is why it is not octahedral molecule. Next question is, what is your CN? And for that, if you look very carefully, all the nitrogen over here they are all in the forefront. So, now if you put over there and rotate 120 degree, they are going to remain on its own position. Similar things are following with the oxygen, they remain on the same place. So, that is why with that respect we can say yes, we actually contain a CN and that is C3, very much similar to the previous case. Now, the question is, do I still have the 3 C2s perpendicular to the C3 present over there or not? Previously we found that it was actually present in this particular direction. So, if you rotate the C2, oxygens were exchanging places, but now because I have nitrogen versus oxygen, so they will exchange places. So, that will not be symmetric. So, there is no C2 present in this molecule. So, this is answer is no. Sigma H, which should be perpendicular to the plane of rotation, and I also do not see it, and 3 number of sigma V's, sigma D's, that we also cannot see. So, with respect to that, this molecule only has C3, nothing else. So, this belongs to a point group of C3. So, if you have a C3 molecule, it is going to be chiral, and that is why this molecule will be one of the enantiomer. And as you see, we are rotating front to back portion for this molecule, nitrogen to oxygen, nitrogen to oxygen, nitrogen to oxygen, is rotating this way, left hand side. So, it is a lambda isomer. Then the question is, what is the mirror image of that? So, let us draw that. So, if I am doing a mirror image over here, let us consider this particular structure of the molecule as the original structure. So, nitrogen comes here, this nitrogen will come on the other side, this nitrogen remains at the same position, this oxygen remains as it is, and what we are left with, one of the other oxygen, this one. And over here these are the connections, and from here we can say nitrogen to oxygen, nitrogen to oxygen, nitrogen to oxygen. So, it is actually writing other ways. So, it is actually delta isomer. So, this is what is actually happening with the glycinate ligand. Glycinate versus oxalate, the difference is because you have now 2 different atoms as coordination site. For the glycinate, it is actually going to a little bit lower symmetry. So, that is, it is C3. On the other hand, if you look back to the iron oxalate, that belongs to a D3 point group. So, which is actually higher in symmetry. You have 3 extra C2s perpendicular to C3, which is absent in the case of glycinate. Now, the last portion, we will discuss about this particular molecule you all heard of, H2O2, hydrogen peroxide. So, what is the structure of hydrogen peroxide? So, as you know, it has oxygen-oxygen bond and 2 hydrogen-hydrogen bonds, but how that particular thing is actually oriented, they are not planar. So, what is the structure? The structure of the H2O2 molecule was described as an open book structure. So, say this is the base of the book and is open such a way that you can see both this particular side. Okay, so, this is the front side. So, this is how it looks like, and over there the oxygen bond over there sits over there for H2O2, 1 hydrogen in one of the page, 1 hydrogen in the other page. So, this is the actual structure of H2O2, and over here, although we said earlier this open book structure, now you understand why, because on the border of these 2 planes oxygen-oxygen bond stays and OH bond goes to each of the other planes. So, this is what we say open book, and nowadays we understand better say like open laptop kind of structure. Now, what is the point group of this molecule? To figure it out, what we do, we try to look into through this oxygen-oxygen bond. The front oxygen I am drawing as a line, a dot, and there is the hydrogen, these are H1, and say this is the H2. The backward oxygen I am showing you as a circle. So, this one is actually a little bit tilted, so somewhere around here. So, this is the structure of the molecule when you are looking through this oxygen-oxygen bond. Why I need that? Because now if I want to find out the point group, I say whether the molecule is linear, the answer is no. Tetrahedral or octahedral or any cube group, no. CN, do you have a CN? So, for that we are doing this particular set of the molecule, and over here you can see this is the front, this is the back, and over here if I rotate C to 180 degree, what will happen? Front oxygen will go to back, back oxygen come to the front, and this hydrogen will come over here, this hydrogen will go over there. That is the motion you are going to see. So, that is why we have a CN and that is C2. Next question is, do you have 2 C2s perpendicular C2? And answer is no, there is no perpendicular C2. If it is there, it has to be somewhere there or somewhere there, and there is nothing. Next question, it is sigma H containing molecule or not? Sigma H molecule has to be somewhere perpendicular to it, and you can clearly see it is not. 2 sigma V's does it present? Now, sigma V are 2 planes which are going to bisect this molecule, and the only plane we can see that is bisecting the molecule is none. So, there is no such sigma plane present in this particular molecule. So, neither sigma H nor sigma V. So, if this is the case, then we say the point group of molecule is actually C2. So, that is the point group of the molecule. So, if you have a C2, then the molecule should be chiral in nature. So, H2O2 molecule should be chiral in nature, but when we go and try to find H2O2, we found this molecule is actually not chiral at all. Now the question is why it is not chiral. So, for that what we are going to do, draw the mirror image of this particular molecule. So, over here this is the front carbon, this is the front oxygen, back oxygen, this is the front hydrogen, this is the back hydrogen. So, obviously they are not fitting on each other. Now, if I want to go from this structure to this one, how I should do? And that is doable if there is a bond angle rotation. So, let me draw this open book structure one more time. So, this is where we started with, and after the mirror image, that is how it is now. Now, to bring them in the similar way, this oxygen band has to rotate so that this one come over there, this hydrogen goes on the top, that is the structure. So, that means there needs to be a rotation, this hydrogen comes over here and this hydrogen goes on there, and that is possible with a oxygen bond rotation. And this oxygen bond rotation happens because it actually requires very low amount of energy, and this particular bond rotation, or as we say fluxionality in the molecule, ensures that this particular molecule of the enantiomer will look very similar to the original one. Because in the previous cases when you are taking the mirror image, we are not allowing to do any particular change or fluxionality. Over here we are allowing to change them, the bond angle, bond length, all those things. And if this is actually happening, we create a fluxionality, and that actually kills the chirality, because now the enantiomer is not going to be staying as it is going to change to the original structure. And over here we say this fluxionality is actually the important factor which ensures that the chirality is not seen. So, that is actually killing the system. So, with that we would like to close over here. So, today we go through 3 different examples. One is the iron oxalate, one is the iron glycinate, where they are D3 and C3 point group each other, and we found both of them are chiral. We also know the nomenclature delta and lambda isomer. Then we come to this curious case of hydrogen peroxide, very common molecule, and we find out that this is actually a chiral molecule, but due to this oxygen bond rotation, this molecule lose its chirality because it goes back to this original position. And with that we would like to conclude over here. We will continue with respect to the other applications of CD spectroscopy in the next class, along with the molecular origin of CD spectroscopy or circular dichroism spectroscopy. Thank you all.